Alright, so first of all, let's have a clarification for the last lecture. So we said that the equation for the current sensing delay should be this one. If you do the approximation, make the RL approach 0, then you will get the following equation. So this should be the correct one. This is different from the voltage mode. So this is just a clarification for the last lecture. And then we discuss about this particular design for the 32 gigabit RN chip proposed by SanDisk. And this is a two-layer cross-point array. And the peripheral circuits are underneath the cross-point array. And here, this is like a bay or bank. And then within the bay or bank, we have the blocks. And one block is like 2K BL times 4K WLs and two layers. And then in one bay, although we have like 128 blocks, the whole bay only has 64 sense amplifier. So that means we have to share the amplifier from other between multiple blocks. So here, for example, if you sense the sense amplifier probably are distributed. And even you activate one block, you want to get 64 bits, you have to borrow the sense amplifier from other arrays. So this is one limitation of the design. And one of the reasons is that if you look at the cross-sectional view image, so the cross-point array in this case has very high density because the pitch is like 24 nanometer, half pitch is 24 nanometer. But the peripheral transistors use old technology node. You look at the size, they didn't disclose the exact tech node, but from this scale, we can guess it's about like 130 nanometer or 180 nanometer. So in other words, in this particular design, the array in terms of area is pretty small, and then the peripheral circuits, because each transistor is much larger. Therefore, we cannot have too much resources or areas for the peripheral circuits because each individual transistor takes so much space compared to the memory array. Therefore, they have to share those sense amplifiers across multiple blocks. So let's look at the exact sensing scheme for this cross-point array. So here, this is a cross-point array, and we have those selected cells. So in this case, this is like voltage sensing. So we are going to pre-charge the selected bit line to be the V read. And then selected word line, you will make a low voltage, and this VUB could be 0. You can think this is like low voltage. So then there will be current flow on those selected cells. And then for the other unselected word lines, then we have to bias to be V read. Try to minimize the current through those unselected cells because both ends will be V read. But of course, this V read on the bit line will decay over time. So as time goes by, there will be current charged back to the bit line, which is undesired but with the help of the selector, this chargeback current can be suppressed. So if you think about this, so this is a selected cell, and here you ground the selected word line, and then you pre-charge this bit line to be V-read, and then this is unselected cell, so you bias this to be V-read. So ideally, then the current will flow this way. This current will discharge this BL, and of course, depending on the resistance, high or low, then the discharge rate will be different. But as this discharging occurs, then the voltage of the V-read will decay. So if you look at those two terminals here, this V-read will decay. That means will minus some delta V, right? So then you have current charge back. This is undesired, and we need the selector to cut off or at least suppress this current. And then this is like the sensing scheme, and then the bitline voltage here will be connected to this sensing node by this clamp transistor, and then this voltage will be compared against the reference voltage. So here, this is a waveform of the V-sense node here. So after the pre-charge goes off, then the bitline will start decaying, and depending on the cell strong or weak, strong means the low resistance state, you have high current. Weak cell means high resistance state, you have low current. So then the decay rate will be different. And in the middle, you can have some reference cell, which you could program to be halfway between the high and the low resistance. Then this can be the ref cell, and this ref cell can be attached to the VREF as a VREF. So then here, you will enable the sense amp. Here there must be an enable signal here to compare your bitline voltage with this reference after certain delta t. So this is like the voltage sensing scheme as we discussed before. And in this particular design, the reported sensing time is about 1 microsecond. But this is for individual, like a block sensing. But the total read time or read latency is about 40 microseconds. Because we shared those sense amplifier, you have to borrow other sense amplifier from other array, which is far away. Then there will be parasitic RC delay, make the total read latency small. Total latency large. So I would say this is not a perfect design for this particular technology. One of the limitations is that the peripheral circuits use very old technology node, therefore limit its area and also performance. So any questions? Then we will have a tutorial for this NV scene simulator. And you are going to use this simulator for your homework 5, which we haven't posted yet. But after you are done with your homework 4, then we will post the homework 5. So basically you will use this simulator to design some emerging memories array. And why do we need the circuit level simulator tool? So for different memory designs, before we do the real tape out, then it's necessary to explore the system or bank level organization. And we want to know the area and the read-write latency, read-write energy, and leakage power, given different design options. Because for the memory design, you can have different options, like the subarray size, number of blocks, and how many cells you read or write simultaneously. So there are many choices. So the research community then developed some of those simulators to do this design space exploration. And there are some pioneering work. For example, this cacti was originally developed by the HP Labs, and the developer originally was John Lupi, who later joined Google and designed the first generation of TPU. So the cacti was widely used for the SRAM and EDRAM cache design by the research community. And if you are doing some computer architecture memory cache design, then probably you will use the cacti. And there are some extensions from the cacti for the DRAM memory. But for the non-volatile memory, this is some emerging field. Therefore, we need some dedicated tool for the non-volatile memory as well. And but the principle are borrowed from the pioneering cacti for the SRAM or the EDRAM. So here the tool was developed by Professor Yuan Xie's group at UC Santa Barbara. And here is a subarray model for the memories. And we have those generic building blocks as we discussed earlier. And like those peripheral circuits, row decoder, word driver, mux, sense amp, and output driver. Sometimes you have the pre-charge equalization circuits. And then the memory array will have many choices. So we want to build some models for those modules in the memory subarray. And there are many design choices. For example, for the transistor, as we discussed before, for any tech node or process, we may have a variety of those transistors, like high performance transistor, low power transistor, low standby power transistor, because the foundry will offer different kinds of transistor with different VTH, right? If you want high performance, the threshold voltage will be low. If you want low power, then the threshold voltage will be high. There will be trade-offs between the I-on and I-off, as we discussed before. So for different memory arrays, depending on your target, you may choose different types of transistor for the peripheral circuits. And also for the memory array, we discussed, then we have the MOS access, means 1T1R kind of structure. You have one transistor, one resistor. Or we have the cross-point array, like we discussed before. Probably here you need a selector. And also the sense amplifier, as we discussed, there are two major groups. One is voltage sensing, the other is current sensing. And then those drivers, as we discussed earlier, will have different optimization goals. You can optimize for the area. You have fewer stages of the inverters. Or you can optimize for the latency. You spend more stages, but the latency can be minimized by optimizing the logic effort in the design. So there are many design choices. that means many combinations, right? If one variable has 3 possible values, then there is a large design space if you consider all the possible combinations. And another variable for the subarray will be the subarray size. You design the circuit like 64 by 64 or 256 by 256. So you have another degree of freedom of the design. So here the model is not space simulation. So it uses some analytical equations to estimate like those area latency power for those modules like decoder, mux, sense amplifier, and so on. And then they just simply add the module level energy together for the total energy of the chip, add the module level area together for the total area of the chip. And for the latency, just look at the critical path, what are the bottlenecks of the latency, and then add those latency for the critical path. So here are some validation of the tool or model prediction from the tool versus some reported actual chip performance. For example, this is a 64 megabit MRAM, magnetic random access memory, in ISCC 2010. And the projected area is close to the actual area, and latency-wise is also close. And also another validation is to this 512 megabit phase change memory. And then there are some errors for some of those parameters, but without doing the actual tape out, you can project the performance by simply run this tool. So let's have some exercise for the design space exploration using this NVSync tool. So here, this is the application. And in this particular example, we want to design a most accessed, that means 1T1R, based R1 for the last level cache. And first of all, I would ask the question, do you think this is a, let's say, a viable application? Do you think the R1 is good for this application? R1 could be slow, but that's not the major limitation. Endurance is a problem, because for the cache, and you have done your homework before, right? So for the cache, the endurance requirement is pretty high. And for the R1 technology, probably you cannot get that endurance. But this is just an example. Okay, if you want to do this design space exploration without considering the endurance, then let's do this exercise. Because you can change this to MRAM. Because in your homework 5, we're asking you to do the cache design with the MRAM, which could be more variable because MRAM can provide more endurance, like 10 to the power 12 or 10 to the power 14 even. So anyway, so this is just an example how to use the tool and what can you do with the tool. So here you identify the process technology load, and in this particular example, we choose 32 nanometer. And then this is your design target. You want to have a 8 megabytes cache for the last level cache. And cache has certain associativity. So we didn't discuss this, but if you go to the computer architecture class, then they will talk about what is associativity. So the cache, due to the mapping from the logic space to the physical space, there is associativity concept. We will not go into that. This is due to the address and how do you do the mapping. Okay, so then your design can be area optimized, leakage optimized, or speed latency optimized. So if you use the tool and run a lot of simulations, basically you go through the combinations of all possible variables, then you can get the design point for those area optimized, leakage optimized, and speed optimized design points. For example, here in this 3D space, the area optimized will give you the smallest area, and but the leakage might be high, and speed optimized will trade off with larger area, but the speed-wise will give you like lowest read latency. So let's look at the design options in the NVSync tool. So at higher level, you want to identify the capacity of the total memory, and you want to design it as a run or as a cache, because if you design as a cache, then you need to define this associativity. And then I/O width, that means the interface number of bits, like 8 bits or 16 or 64. And then at the subarray level, then you have to define the subarray size, cells per bit line, cells per word line. So basically like your 32 by 32 or 128 by 128. And then the wire model, you need to define the local interconnect, semi, or the global interconnect. So this is related to what we discussed before. If you do local interconnect, you have to sense the data at the subarray level. If you do global interconnect, then you will have some partial swing of your signal on the global interconnect before you reach to the sense amp, which is typically shared among multiple subarrays. And then transistor model, as we just discussed, you have different choices for different VTH. And the memory types, here it supports SRAM, DRAM, EDRAM, also number type memory like STT-MRAM, phase change memory, RAM. And then for those each individual memory cell, you have to define the cell size in F square. Right, so SRAM, for example, you 160 F square, and the RAM maybe like 20, 30 F square. And the cell aspect ratio, that means the cell size is like for SRAM, it's like as we discussed before, like this 8F by 20F. So you have to specify the layout. And then here is like 1T1R or cross point for the emerging number line memory. Of course, SRAM, it will assume 60 SRAM by default. And then there are other options for the mux and the sense amplifier. Current sensing or voltage sensing will matter or not. And then the driver, as we discussed, the different kinds of driver options. Latency optimized, area optimized, and or more balanced design. And then at the bank level, the number of subarrays and the interconnect style is more like a H-tree or it's more like a bus. So you need to define those options. Since we will have so many options, if you think about the design space, it will be huge, right? It could be like 1,000 combinations if you vary those numbers in each of the options. And then this is the result after the simulation. Then you can generate the spectrum of the design space. Each point corresponds to one particular design combinations of those like subarray size or the the transistor type or voltage sensing, current sensing. So you vary those, and each design point will correspond to a particular combination of those options. And here we show the read latency versus the density, like a kilobyte per millimeter square. And here we have so many points. The reason is we have so many variables, and you sweep the variables as a combination. And here you can see that from the latency wise, read latency, S run, this like triangle pink, typically lower latency, like what this is like 1 nanosecond, right? This is 10 nanosecond, this is 100. So S run is like 1 nanosecond around that. And the memory density, of course, as a same technology load, S run will have lower density, right? Each cell is larger. So the S run is in this range, right? And then R run, the two flavors of R run, 1T1R or cross point, but mostly they will have larger read latency, like here, like tenths of nanosecond. So as some of you point out, the R run not good for cache, right? Because the latency, even before you run the simulation, you will know, right? R run generally will have higher read latency. And then here the 1T1R, like the cross points. And here are 2 points for this is ED-RAN, this is off-chip DRAM, standalone DRAM. So you know the space of your design. And also here the write latency. And the SRAM typically much faster, like around 1 nanosecond or 2 or 3 nanoseconds. But the RRAM here limited by itself. This is limited by the physical property, how fast you can write the RRAM cell. So the write latency for the emergent non-volatile memory is more related to the physics of the memory cell. But the read latency is mostly affected by the RC delay and your sense amplifier design. Right? So anyway, so this is like the spectrum of the design space without considering the endurance. Okay. So if you assume R has, in the future, if can have good endurance, then this is how it look like, or how does it compare with the SRAM for the cache. Then you may wonder, then will this be useful? So before we address that question, so here is let's say here are a few design points, so selected from those spectrum. Here are a few design points if you want to optimize for certain metrics. So you will pick the point from the spectrum. For example, here, if you want to optimize for the area, this is the same design target, 8 megabyte R1 cache. If you want to optimize for the area, then you get the smallest area. But then those are the properties that you trade off with the small area. Your latency may be like hundreds of nanoseconds. And here are the design choices you need to do to reach this smallest area. You need to use cross-point array. Subarray size needs to be large. You need to use non-H tree. That means you have to share the sense amp and use external sensing. And also the sense amp, you have to use a current mode. So if you do that, then you get this smallest area. And similarly, you can look at other properties. If you want to optimize for the read latency, then the area needs to be significantly increased, and read latency can go down to like 1.7 nanosecond, which is close to the S1. But then the trade-off will be smaller subarray size. This also explains you have larger area, and also you have to use H-tree, current mode sensing, and internal sensing. So this gives you some of those extreme cases for certain metrics. So any questions so far? Okay, then next we will address the question whether this ARM-based cache would be useful or not, assuming endurance is not a problem. Then to address this issue, you have to do a system level benchmark. Because what we discussed so far, this NVSyn, is a circuit level model. It only generates the circuit level specs, such as the chip area, read latency, write latency, or the power. This is not the system level performance, because at the system level, you will use that cache in a processor, right? You need to consider the workloads and the processor's spec. So to do that, then we have to run the system level benchmark, and assuming the R1 is used for the L3 cache in this example. And this is done with this Gen5 tool. I don't know if any of you heard of this Gen5 before. If any of you have taken the computer architecture courses, they didn't use this. Not good. So if you look at the computer architecture conferences, like ISCA, Micro, you will see a lot of papers using this Gen5 simulator. It's a cycle accurate and instruction-based simulator for CPU. I guess they have extended to GPU as well. Anyway, so for the original version, this is a simulator for GPU for CPU. So let's look at the parameters you have to define in this Gen5 simulator. So you have to define the clock frequency for your processor, and then the number of core, in this case 8 core, in order of those instructions, and then define the cache hierarchy. And here the L1 cache, we have S1. Of course, you can put R1 to the L1, which will not work, but as a simulation, you can try and see what will happen. And then you can vary the L1 cache capacity, and then the associativity for your 8-way. And then similarly, L2, you can define it as S1 or R1, and L2 has this kind of typical capacity. And then similarly, L3. And here our interest is to use R1 as L3, because we know for sure L1 or L2 will not work. But let's look at if you can have L3 cache with those capacity, what will happen? So the relationship between the NVSyn is the output of the NVSyn will be the input of the Gen5. So the output of the NVSyn is like the L1, L2, L3 cache, area, read latency, write latency, and the power. So those will be the input parameter to the system level simulator Gen 5. And then the Gen 5 will run typical workloads. And then this is the output from the Gen 5 simulator. The output from the Gen 5, the most important metric will be this IPC. That is instruction per cycle. Because from the computer architecture point of view, how good or how bad your processor is depends on this instruction per cycle. Per clock cycle, how many instructions you can execute on the processor. This is an indicator of the performance of the processor. And here we have so many design points, right, from here. And this will be the input to the simulator of Gen 5. And then this will be the output from the Gen 5, which is the IPC as a function of the system level power. So here you see several design options. So the first one, this one, is this is the baseline. You use SRAM for L1, L2, L3. And then this is, of course, for SRAM, you can vary those parameters. So still you have a range of the IPC. Because for the SRAM, you can still vary like the kilobyte or megabyte for different levels of the cache. So you still have this different design options for SRAM. And typically SRAM will have higher IPC, as you see here, because SRAM is faster, right? But SRAM's power, if you consider the leakage power in the real workload, then the power of SRAM, not only SRAM, this is system level power, including your ALU, your compute, and then the cache and also the main memory power. So this kind of processor needs like 40 watts, but you do get higher performance. And then the second design will be this one. We only replace L3 with R1, and that will give you this curve. So here you sacrifice a little bit IPC because R1 is slower, most of the R1, right? The read and write latency will be slower. But from the system level, you only sacrifice like 10% of the performance. But here, before it sharply drops, then you can reduce the power down to like system level, down to 25 watts. This is because the workload is a mixed workload. Sometimes you do write-intensive applications, sometimes you do read-intensive applications, and sometimes the system is on the standby, in the sleep mode. So those are the mixed applications. So especially during the standby, the SRAM consumes unnecessary power, right? But for the R1, you can power off that bank, or you can power off that cache. Your data is still there, right? So then you can greatly reduce the system level power. And then let's look at the last design, which is not realistic. You use R1 for all the 3 levels of cache. Then the IPC will hurt or not. And the benefit of the power reduction is not that great, so this is not so good. your IPC will drop a lot. So here, the second design is more balanced. Of course, from the performance point of view, all SRAM design will be the best, of course. But if you want to minimize the power, then you can trade off the performance with the power, and you can replace the L3 with R1, especially when you have a large cache. I believe some of the better designs is to use a huge cache, if that is possible, in the R1, then you want to choose that. Because if you have large cache on chip, you don't need to fetch the data from DRAM so often. Because as long as you go off chip, fetch the data from the DRAM, the energy will be much higher than you fetch the data on chip. So the goal is to have an extra large capacity of the last level cache. And if you use SRAM, then the leakage of such large capacity cache will dominate the power, especially when your application is mostly standby, then it's not so good. And here, this is another trade-off between the IPC and the total area of the chip. And similar trade-off, like SRAM design, you have larger chip area but better performance, and R1 you have smaller chip area and then reduced IPC. Of course, those conclusions can be speculated even before you run the simulation. But if you want to get some quantitative, like how worse the IPC will go if you change to R1, if you want to know some quantitative, like 10%, 20% degradation, then you have to run this kind of simulations. Of course, as I discussed earlier, so the initial assumption using R1 is not very good because of endurance issue. But you can imagine if we change this to STT-MRAM or SOT-MRAM, as we discussed later in more details, this might be some interesting problem or applications to look at. All right, so here this is a GitHub link for the tool, and we actually provide you in homework 5 already pre-download version, so you don't need to go to this website. We provide you a local version of the codes. And then if you want to know more details about the tool, you can read this paper published in the transaction on TED. And this tool, as I've said, borrows the principle from the cacti, and with the collaborations with Nong Jupi, who is the designer of the Google's TPU. All right, so in the next few slides, I will quickly show one example of the code, just to have a tutorial for you. So here is the configuration file, and here you need to define the input to the NVSync simulator. So here, the design target, for example, is a RAM, could be like a RRAM, MRAM, of exchange memory, or SRAM. And then here, you want to design some of those parameters, because it can automatically choose the data point, not the data point, and the design point to meet those optimization targets. Of course, if you don't specify that, then it will run all the possible combinations. But if you specify the design target, then after they run all the combinations, they will quickly extract which combination will give you the best rate EDP, like the energy delay product. And then you need to choose the process technology node, like in this case 22 nanometer. And then here are the design specs of your target. For example, here we want to design a 2 megabyte run. And then the I/O width is like 128 bits. And we want to design using the high performance peripheral circuit transistors. And then here, actually I don't know the details of this wire type, but here the wire repeater, repeated long, there's no repeater. So if you have a long wire in the interconnect, if you want to minimize the latency for the interconnect, typically you are going to insert some repeaters between the long wires. Repeaters, very simple, just two inverters to buffer the signal. And then here are like the bank organization, like you define this is like H-tree routing and the internal sensing. That means the sensing is happening at each subarray. And then here, this is the you need to input another file called something.cell. So this example is like srun.cell. In that cell file, you would define some parameters for the srun bit cell. And in your homework, you are going to do with this sample stdmrun cell parameter. And also the chip temperature can be specified. That is your operating temperature. This is higher than room temperature. So room temperature, is 300 K. And then here there are like a bank level organization. So this is within the bank. I think this is within the bank. You have 4x4 like a match, and you only activate 1x2 at the same time. And then this is within the match. You have 2x2 subarray. So you can change those configurations. And then the max sensamp. This is how many sensamp share one. This is how many columns share one sensamp. So those are the parameters you may change, but I don't think in your homework you are going to change those higher level properties. In your homework, I believe we ask you to change mostly the parameters in the cell file. And this is the cell file, sample stdmrun. So you need to specify the cell area in terms of f square, and stdmrun, we discussed briefly earlier, the cell area could be large because the 1T1R for the stdmrun, you have to pass large current to write the cell. So the transistor width could not be minimal. You have to increase the W/L of that 1T1R transistor. Then the cell area could be large. Of course, it will be smaller than SRAM. And then here you need to define the on and off resistance of the stdmrun cell. And typically for the stdmrun, the on-off ratio is small. Here only 2. You see the on and off only differ by 2 times. And then current mode sensing and the read voltage 0.25. And then there are some other parameters. The set and reset, that means the write current and write latency. For the set and reset, you write 1 and write 0. And then it is 1T1R based cell. So here are some parameters you need to define in the cell file. and then you click Run button, and then it will generate the output for your particular input combination. And this is a sample output format. First of all, it will repeat your assumptions of your input, like those parameters for the cell. It will repeat, and then it will also repeat your design specs. You want to design, in this case, 128 kilobyte run, and also it will repeat your configuration here. In this case, the subarray size is 512 by 512. Those are the inputs you need to specify earlier, but here in the output report, it will repeat what you used for the input. And then this is a real result. So it will report the total area, and then it will have a breakdown of the area at the mat level, subarray level, and it will calculate the array efficiency, the memory cell area divided by the total chip area, as we discussed before. And then the time mean, like read latency in total, in this case, like around 2 nanoseconds, and it will break down into the critical path. Like the decoder takes like 80 picoseconds, and the bitline sensing is like bitline like delta T from the bitline is like 15 picoseconds, and then the sense time latency will dominate in this case. So it will have a breakdown of the latency. And also, I believe there are breakdown for the power as well. So here I didn't show that in the slide. All right, any questions? So that's a very good question. How long does it take to run those data points? So as I said, this is not a SPICE simulation. If you do a full SPICE simulation for the whole circuit, whole memory array, it will take you hours or even days. This is an analytical model, so that means equation-based. So if you run a single point, you can get it almost in like within a minute. So if you run the whole spectrum, it will give you may take like a few hours or 1 day with the full spectrum. But it's reasonable for this kind of design space exploration. It's not as accurate as your SPICE simulation, but it can be much faster. So this is the main purpose for the system designer or the computer architect. You want to know the higher level design choices before you do the real tape out, right? So then you want to know what is the trade-off between the array subarray size. You want to define those parameters first, and then after you use this tool, then you narrow down your design space to a few points, and then later you do the full design. Like if you do the digital design, you go through the synthesis and the placement and routes, and then you do the post layout simulations, right? So this is after you narrow down the design space. But at the very beginning, then you have a wide spectrum. Then it's unrealistic to run the full design. So that's why this is for design space exploration. All right, any questions? Other questions? If not, I think today we can end earlier.